time we discussed partial summation. Sometimes also called obel summation. And applications, right? We discussed that. So let me refresh your memory. So we have a sequence of numbers, a sub n. And we define capital A of x to be n less than x a sub n. And we take a differentiable function on the positive real line, let's say for on R plus positive reals, and we consider the sum a sub n f of n, like so, and a very elementary calculation shows that this is the same as a of x f of x minus the integral from 1 to x a of t f prime of t dt. So in other words, the beauty of Abel's lemma is that a sum of the form summation a n f of n, which is a finite sum, is changed into an integral, provided you know something about a of x. That's the beauty of this particular formula. Okay, we applied this to a variety of special examples, and most notable was we proved that Chebycheff's theorem using this we proved that summation p less than x log p over p, where p is a prime, p is prime, p prime, is equal to log x plus something bounded. We proved that using the von Mangold function, if you remember, lambda of n defined as log p if n is a prime power and 0 otherwise. And the unique factorization property of natural numbers translates neatly into the equation log n equals summation d divides n log lambda d. And we use this fact along with the fact that summation log n less than x via Abel's lemma is x log x minus x plus O of log x. So this, on one hand, we could use Abel's lemma to deduce this. On the other hand, inserting this particular expression into the summand here and interchanging and doing the needful allowed us to deduce this remarkable identity. And then I showed you last time how this can then be used to prove Chebycheff's theorem that let pi of x be the number of primes less than x. Chebycheff proved that there exist constants A and B positive, so that ax over log x is less than pi of x is less than b x over log x. In other words, the prime counting function grows like x over log x. That's what he managed to show. He managed to show this using this. Of course, now I twisted his proof a little bit. I didn't exactly give his proof. I gave my version of it. The first upper bound was fine. The second lower bound, I didn't follow his method. And actually, you can get it from here. And I showed you how that's done. So this is what he managed to do. And of course, he tried very hard to prove what's called the prime number theorem. This is around 1840, 1850, or thereabouts. So Chebycheff tried very hard to prove the prime number theorem. The prime number theorem was a conjecture of Gauss. Says that limit x goes to infinity of pi of x divided by x over log x equals 1. That's the conjecture. Now Chebycheff, because he tried very hard to prove this theorem, he was trying to refine the constants in a succession of papers. He was trying to show better and better constants. He was getting awfully close to 1, but he wasn't quite there. And he managed to show, using this particular fact here, that so Chebycheff showed if limit exists, then it equals 1. The limit is 1. So he managed to get very close, but not right there yet. And how would you do this? How did he do this? Well, as I mentioned last time, the study of pi of x, the prime counting function, is a little difficult to do because of its raggedy nature of counting. Every time you hit a prime, you put 1, otherwise you put 0. It's a little raggedy, okay? So it's better to perhaps weight primes by log p and try to count those. So what he first showed was using Abel's lemma, or using partial summation, Chebycheff showed that the study of pi of x being asymptotic to x over log x is completely equivalent to saying theta of x is asymptotic to x, which is completely equivalent to saying psi of x is asymptotic to x. Where, what are these functions? Where theta of x is log p, p less than x, where that means I'm summing over primes and I'm weighting each prime by log p. And psi of x equals n less than x lambda of n, where lambda of n is this one Mongold function. And what's the difference between this and this? Well, this includes prime powers and this doesn't, but the prime powers count for very little with respect to x, of course. So they can, their contribution to the sum is small, and therefore the whole business of trying to prove that the prime numbers behave this asymptotic law is completely equivalent to proving this asymptotic law, which is completely equivalent to proving this asymptotic law. So in other words, if I'm trying to show that this limit exists, that's equivalent to showing this limit exists. Okay, so we will, or this limit exists. So we will now look at this equivalence. So let's try to show if the limit exists, the limit is 1. Suppose, so what I'm trying to say is, suppose, let's prove the following theorem. So suppose, and this is probably a good exercise in how analytic number theory works, so I'll do a little bit of it. So suppose limit x goes to infinity, theta of x over x exists. Okay? Then the limit is 1. Then alpha equals 1. Last time I introduced the big O notation, which was very convenient for calculations. This time I'm going to introduce little o notation. So we say, it's very convenient to use it, we say f of x equals little o of g of x. I put a dash under the o because sometimes people make o's big and then that would be confusing, right? So when I put a little dash, at least I know I'm talking about little o. So we say this if limit x goes to infinity, f of x over g of x is 0 as x goes to infinity. Yeah. Okay, so for example, we have we have log x is equal to little o of x, right? Because log x by x goes to 0 as x goes to infinity, etc. Now we can express this limit here in terms of the little o notation. What this says, star says that theta x equals alpha x plus little o of x. Because when I divide by x, theta of x divided by x is equal to alpha plus little o 1. What is something little o 1? It goes to 0. That's what little o 1 means, okay? So that's another convenient way of rewriting a limit as an equation. So you can see the power of the symbol. Again, I told you the power of symbology in mathematics and probably in life is that it's a very powerful psychological factor in thought, in human thought. So, okay, we have this. Now let's look at this equation here. This, let's call this double star. Let's look at that equation. So, double star by partial summation we can rewrite this thing as keeping in mind that I'm going to use my sequence to be log p and my function f of t to be 1 over t. So that would be theta of x divided by x minus the integral from 1 to x theta of t over, well, the derivative of 1 over t, that's plus t squared dt, right? So I rewrite it using the partial summation technique. That gives me one more relation. See, on one hand, I know that it's equal to log x plus big O of 1. On the other hand, I have my connection to the theta function here, and I'm going to try and exploit that. Now, remember that we already showed last time that pi of x being O of x over log x is equivalent to theta of x being O of x. We've already shown that. So this guy here is O of 1. It's bounded. Okay? So at least this is now tallying here. Okay? There's a bounded quantity. So this is not going to do. So the main term of this thing is log x. So the main term really should be coming from here. Now I'd like to plug in theta of t is equal to alpha t plus little o of t into here. And let's just do this mentally for a second. If I plug in theta t to be alpha t plus little o of t, I would get alpha t plus little o of t divided by t squared. That would be alpha over t dt, and alpha over t dt integrates to alpha log x. Okay, so at least, so if that's the case, well, there's a log x there, therefore alpha better be 1. So that's kind of the proof, but there's something wrong with that proof. Something wrong is how you treated the little o factor. Okay, so it's not quite right to say that this is equal to the integral 1 to x alpha t plus little o of t. You should know how to use this little o symbol carefully. Remember what little o means. It means as x is going to infinity. So there's a little bit of a problem in the initial ranges, right? So you really can do this. This little o of t is only when the argument is going to infinity. So what you really should do, so let me just finish this off. So this guy is equal to alpha log x, and what looks like little o of log x. That's what it looks like. That's almost right, as I said, but this really should be split up into 1 to y and then y to x. And I'm just going to leave it to you to do at home. Okay? And y is what? Y is going to be some parameter to be chosen later. And when you, so that y is going to be a certain function of x, which will tend to infinity. So on this part of the integral, you can use this little trick, because the little o of t is okay, because that's little o of t as long as t is going to infinity and all the arguments are going to infinity here. But on the initial part, you have to be you have to use the some sort of crude estimates, and get away with that. And there you would use the fact that theta of t is O of t, and therefore it's O of t over t squared, but then you're going to get an O of log y. So this will give you something like O of log y, and this will give you alpha log x over y plus something small, so that's okay. And then if you it turns out that if you choose, well, this is not the only choice, but if you choose y to be like e to the root log x, then the log y here will be root log x. So this is y. Log y would be root log x. So that the contribution from the y factor is substantially smaller than log x, since the main term on the left-hand side is log x, and the other term here is alpha log x, you then deduce alpha has to be 1. Okay, so this is a little bit of a trick exercise in analytic number theory, which you should master in how to use the little o symbol. Okay, so but that's the proof. That's the proof of Chebycheff's theorem that says if the limit exists, it has to be 1. So the whole business of the proof of the prime number theorem is now reduced to showing the existence of the limit. And you may wonder, how could that be so hard? And it is. That's where the hard part is. So sometimes, very simple things can be very difficult. Simple things stated can be very difficult to prove, right? So are there any questions about what I said so far? Looks okay? Okay. All right, so that's that. As I told you last time, the whole philosophy behind analytic number theory is to use analytic methods to deduce things about numbers, prime numbers in particular. And so far I have confined myself to real analysis, and I'll do that for a while. Maybe next week I will have to move into complex analysis. All right. Now, Abel's motivation for proving his theorem was a question in power series. What was this question? So suppose, so basically let me try to explain that. So suppose is a power series. Is a power series absolutely convergent in mod x less than 1. Okay. Suppose that summation n equals 0 to infinity, an converges. Okay. Then his theorem is limit x goes to 1 from the inside the disk, summation n 0 to infinity, an x to the n equals n goes from 0 to n. You just can't plug in x equals 1 because that silly thing doesn't, it's not defined there, doesn't convert, or you don't know. I mean, you just can't plug in x equals. But he says that the limit actually is fine, provided this thing converges. Okay. Now this is what Abel proved. This is called Abel's theorem, or Abel's lemma, or whatever you want to call it. And this is why he needed to shift. So I'll leave this as an exercise, because for you to prove and to do at home, I think it's useful and instructional. You need to look at partial sums, and you need to create a new power series with those partial sums as the coefficients, and then relate that new power series to the old one, and then I'll leave that as a hint for you to do. But that's basically behind the thesis behind the thing. So what is he doing? He's telling you something about the behavior, based on like the global, from the global behavior, he's able to say something. Well, he's able to say something about the function globally is actually given by this particular series. So, as an example, let's see. Let's look at log of 1 minus x. Right? I mean, this is the expansion for that. But if I change x to minus x, right? So I have a series like this. Okay, now this is valid for mod x less than 1. I'm sure you've seen this in real analysis. But now I'd like to shove in x equals 1. Right? I'd like to say that when x equals 1, minus log 2 equals summation n going from 1 to infinity minus 1 to the n over n. And this series actually converges, but I'd like to know what it is. The answer is log, essentially, well, it's starting at 1, right? It's a minus sign. You're familiar with 1 minus a half plus a third minus a quarter, dot, 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 equals log 2, right? Kind of familiar with that. This is how you prove it. This is what Abel was trying to do. So now notice that here we have a theorem, classical real analysis. Looks like a kind of a by the way theorem, not very terribly important. However, that theorem is not that important as far as I can tell. The main thing is, of course, the theorem is important, but the method is more important than the theorem. And from that, we've extracted this powerful tool called partial summation. And we're just going to use it left and right from now on and see how far this goes. Okay, so it's important to pay attention to methods in proofs rather than the results themselves. That's an indication here. A converse of this type of thing is what's called Tauberian theorem, and those things will also come up later on. All right. Now, in combinatorics, many questions of combinatorics, people use what are called generating functions. You want to study a sequence, A sub n, you concoct this power series and try and study the power series and prove things about the power series and deduce things about the coefficients, correct? So similarly, in number theory, it's often useful to not consider power series, but what are called Dirichlet series. So in analytic number theory, it is convenient to package a sequence into a Dirichlet series of the form summation n going from 1 to infinity, a sub n over n to the s. And study this as a function of s. As a function of s. So the idea is I'm trying to study the sequence ANs, and if I'm trying to study the sequence, it might be useful to study this Dirichlet series, and then try and establish properties of this Dirichlet series, and then from those properties of the Dirichlet series deduce things about the sequence itself. That's the idea. Thus, if we are interested in summation n less than x, a sub n, the philosophy behind analytic number theory is you should study that series. That's the idea. So let me give you some examples. It was Riemann who first pointed out, perhaps, that, or maybe, I guess it goes back to Euler or somebody else, but that in order to study prime numbers, it is useful to study the Dirichlet series summation 1 over n to the s. This series. Now, as you all know, by the integral test, this series converges absolutely for real part s bigger than 1. Now, notice that I've shifted to complex variables. So, as a function of a complex variable, this makes perfectly good sense in that region. Converges absolutely for real part s bigger than 1. And it was Euler who first noticed that the unique factorization theorem, that every natural number can be factored as a product of prime powers uniquely, is tantamount to this equation. I have a product over primes, 1 plus 1 over p to the s, or p to the 2s. So p is prime here, p prime. So as you can see, if you just visualize mentally, I have this infinite product and I multiply the whole thing out. you can see that you're going to get powers of primes as to the nth power, but then each number can only occur once because unique factorization. And every number does occur. Therefore, this 1 is an indicator here that it's unique factorization, and you have n to the s. Okay? So this identity is really a consequence of unique factorization of natural numbers. Now, we introduce this function. This is the Riemann zeta function. I mean, if I said Euler had actually studied this and written this down, and how come we don't call it the Euler zeta function? Why do we call it Riemann? I'll tell you that in a second. Okay. It's called the Riemann zeta function. But the Riemann zeta function is not just this function alone. It really refers to the analytic continuation of this function. Okay, so I'll come to that in a second. But for a real part of s bigger than 1, it's given by the Dirichlet series and by this, what's called the Euler product. Okay? And this Euler product, of course, is a geometric series, so it can be defined as 1 more PDS inverse. Right? It's just a geometric series. And Euler observed that this identity also gives you a new proof of the infinitude of primes. Because if there were only finitely many primes, this product, the limit as s goes to 1, is a finite number, but the left-hand side, as s goes to 1, diverges. Okay? So that little simple observation gives a new proof of the infinitude of primes. You know, I told you last time why in the world, if you got a perfectly good proof that Euclid gave, you take all your numbers, multiply them together, and add 1. That's perfectly good enough. Why are you looking for a new proof? Because that's what mathematics is about. It's not really looking for results. It's looking for new ways of looking at old things. And by learning to look at things in a new way, you discover a new theory. Okay, that's very, very important. So coming up with new proofs of old theorems is also part of research. In fact, most of research does evolve in that fashion. So Euler noted that this identity gives a new proof of the infinitude of primes since we may take limit of both sides as s goes to 1 from the right to deduce the result. In fact, this observation, trivial as it looks, is at the heart of Dirichlet's proof of the infinitude of primes in arithmetic progressions. So Dirichlet actually used this observation. And Euclid's proof doesn't work for arithmetic progressions. If you're trying to prove there are infinitely many primes in an arithmetic progression, Euclid's proof doesn't work. My bachelor's thesis was about when it actually does work. It works if and only if the progression has order 2 mod q. It's very limited. And that's it. That's the end of it. So every time you have a residue class A mod q with the property that a squared is congruent to 1 mod q, you can find some sort of polynomial trick and some sort of Euclidean proof to show that there are infinitely many primes in that progression. But if the residue class does not have order 2 or order 1, you're not going to be able to do it. So for example, if you wanted to prove infinitely many primes congruent to 1 mod q, you can do it because 1 squared is 1. And the proof actually uses the cyclotomic polynomial. So you may want to look that up. So that's about the elementary way. But if you wanted to do other progressions, you really have to go to study Dirichlet series. And this is how Dirichlet hit upon this idea. Okay, so this is an interesting fact. We'll look at it in a second. And one of the things that that Riemann observed is that if you took, so Riemann in 1859, I believe, Riemann obtained the analytic continuation and functional equation of zeta of S. So that's a mouthful. I have to tell you what this all means. So remember that if I have a function which is analytic in a certain region A, so f of S is analytic in a region A, say, and suppose G of S is analytic in a region B, and A contains B, A is contained in B, okay? And if f of S and G of S are equal for all S in A, that means on A, F and G agree, but G is defined on a larger region, we say G is an analytic continuation of F. Okay, to the region B. Is it possible that maybe you can continue it with another function? And the answer is no. And that's one of Riemann's theorems. This is part of Riemann's PhD thesis, actually. All this stuff. The principle of analytic continuation is one of the most profound ideas of mathematics. I would say it revolutionized the whole thing, whole game. The idea of you're trying to study something in a limited region, but you really should be studying something else in a larger region, which happens to agree with the function that you want to study, and all the secrets are contained in this larger object. That is the philosophy behind analytic continuation. And that is what Riemann highlighted in his 1859 paper. He says, you want to study prime numbers, well, this identity links prime numbers to this function. This function is analytic in this region. I will now obtain a new function. Turns out that's what's called the Riemann zeta function. This new function, which you'll still call zeta of S, is defined everywhere except at one point. We'll see in a second where it is, okay? Everywhere. And it happens to agree with this function in this particular half plane. And they said, you really should be studying this zeta function if you want to study mysteries about prime numbers. All the secrets are locked up. Not quite, but they pretty much are. And that's the philosophy behind Riemann's contribution. And I think it's a remarkable idea. So let me explain how one can get how this principle works. I'll give more details perhaps next week about functional equations and so on and so forth, but for the time being, let's just apply our meager knowledge regarding Abel summation and see what Abel summation has to say about this problem of analytic continuation. If I was not interested in this infinite sum, supposing I was only looking at n less than x, 1 over n of the s. Okay, so I'm going to apply Abel to this series. So what does Abel say? Well, what is your AN? AN is going to be 1. And Fn is going to be 1 over n to the s. Okay, do that. Well, I know how to, partial sums of this is that's greatest integer function that we talked about last time, divided by x to the s plus 1, right? Minus the integral 1 to x, fractional part of t, greatest integer of t, over the derivative of, oh sorry, s, yeah. The derivative, the derivative of 1 over t to the s. What is the derivative of 1 over t to the, it's t to the minus s, you differentiated it. It's s, the plus sign, and t to the s plus 1, right? Fair enough? Okay. And then we will play the same game as before. Well, let's not play the game just quite yet. Okay, so here, if I now say that real part of s is bigger than 1, so let's give a name for real part of s. We'll call it sigma. Sigma is bigger than 1. So that means that the absolute value of x to the s is x to the sigma, right? And sigma is bigger than 1. The numerator is x. The denominator is x to the sigma. Sigma is bigger than 1. So as x tends to infinity, this first term tends to 0. So let x tend to infinity. And what do you get? You get n equals 1 to infinity, 1 over n to the s, equals s integral 1 to infinity, right? Let x tend to infinity. And all in that region, real part s bigger than 1. In other words, this guy, this series, which is linked up with the primes, has now been expressed as an integral. That's what Abel seems to be good at. He tells us how to change a sum into an integral. Very useful tool. And now we can do this trick of taking this and then saying that this is essentially t minus the fractional part, right? This is what we agreed on. This is the fractional part. Namely, the part that's between 0 and 1. Now, t over t to the s plus 1 is an integral that you can integrate. And then the other integral is like this, right? The numerator is bounded by 1. Therefore, this integral converges absolutely for real part of s bigger than 0 now. And therefore defines an analytic function in that region. Okay? The first integral can actually be integrated. So what do? T to the minus s, I have to integrate it, plus 1 over minus s plus 1, and I am integrating it between 1 and infinity, right? And keeping in mind that sigma is bigger than 1. At infinity, the first one is 0, and the second one is 1 over s minus 1, right? Therefore, this proves I shouldn't have rubbed that thing off, but let me put it back on again. So on one hand, we have zeta s summation n going from 1 to infinity, 1 over n to the s, product p. So p, I'm just always using it p as a prime, okay, just to keep that in mind. Now, what we've proved, so this is true for real part s bigger than 1. So what we proved, we now proved that zeta s equals s over s minus 1 minus the integral s to 1 to infinity fractional part of t over t to the s plus 1 dt. And now the right-hand side makes sense for a real part of s bigger than 0 except at s equals 1. So this right-hand side is makes sense. So maybe like is analytic for real part of s bigger than 0 except at s equals 1, right? Except s equals 1, where it has a simple pole. Right? There's a simple pole at s equals 1. That's by the way, this is why you need to have a good background in complex analysis before you start analytic number theory. So hopefully you do have that. So this is a simple pole, and the residue, of course, is 1. So we have an interesting, we've obtained analytic continuation of the Riemann zeta function by using Abel's lemma. But we didn't get it to the whole plane. We only got it to this region. This kind of trick to keep on continuing the function for the entire complex plane is an idea that I had developed with my student Kaninika Sinha in her master's thesis, where you can keep on pushing this to analytically continue the whole thing for the entire complex plane, which is different from Riemann's method. Riemann had another method using modular forms theta functions to get the continuation. The advantage of Riemann's method is that he also gets a functional equation. But if you're not interested in the functional equation, but if you're only interested in analytic continuation for the entire complex plane, you can use this method and keep pushing it. And the only more non-trivial factor that you need is the binomial theorem for complex variables. So there's if you're interested, there's a paper that you can study for that particular idea. Okay, so this gives us that continuation that we're looking for. Let me point out that the zeta function here, let's try and see, again, by basic complex analysis, you can show that this infinite product is non-vanishing in this region. Okay? So from star and basic complex analysis, we can show that zeta s is not 0 for real part s bigger than 1. Non-vanishing. So zeta of s is non-vanishing in this particular half plane. Therefore, I can consider its logarithm, and it will be a well-defined analytic function in that region. So log zeta s is well-defined as an analytic function in this region. So let's write down what the log is. Log of zeta of s is given by this log of this product. Okay? And you know how to expand minus log 1 minus x. Let's see. P prime n greater than or equal to 1 over n p to the ns. All right. Now, let's take the derivative of the left-hand side. Because zeta of s is not 0 in this region, I can, no problem putting zeta of s downstairs here. Equals, well, I have this series here, 1 over n p to the ns. How do you differentiate? You can differentiate term by term because this is an absolutely convergent series, and doing so gives you what? Basically p prime n bigger than or equal to 1. When I differentiate, one of the n's cancels on the denominator here, and I'm going to get a minus log p over p to the ns. Okay, take the minus to the other side. Okay, and I have here a Dirichlet series. So this is actually a Dirichlet series. And it is only supported on prime powers. So I can write this as a Dirichlet series. Let me write it deliberately using m instead of n. As a Dirichlet series. And then I recognize that it's only supported whenever m is a prime power. And when m is a prime power, it's only log p up there. So this is nothing but that convenient notation that we had earlier, lambda of n over n to the s. Everybody okay with that? So here is the fundamental connection between prime numbers and the Riemann zeta function. The von Mangold function that you're interested in, because psi of x is summation psi lambda of n less than x, that function that you're interested in to try to prove the prime number theorem, well, that coefficient happens to be here. And so, in other words, minus zeta prime of s over zeta of s is really the series that you should be looking at. But this is all valid for real part s bigger than 1. Right? This series is valid for real part s bigger than 1, but you have this analytic function, but we continued the function to the larger region real part s bigger than 0. And Riemann's philosophy of analytic continuation says that all the secrets of the function that you're interested in are in the analytic continuation. It's like you have to go to Brahmaloka in order to understand life. This doesn't make sense here. You have to go to a higher plane. So that something like that is going on. By going into larger region, you're able to understand something about the prime. Now, notice the key property that we used in deriving this is Abel's lemma. And the fact that we knew what the partial sums of the coefficients were, right? So, remember my aphorism that I talked to you about earlier. Every time you prove a result, you should stand back and see what is the principle, what is the method that you used, and see whether it can be generalized in a much more greater context. Now, if you do too broad a generalization, you will probably mess up everything. but you should step back and see what is it that you did. Now, so what are the key ingredients that went into this proof? Abel's lemma, and the fact that you knew something about the partial sums of, you knew how to count 1 up to, right? So maybe we have a general philosophy that we overlooked with respect to the idea of analytic continuation. So let me try and say that. So more generally, this idea can be generalized as follows. So I have a series n going from 1 to infinity, a of n over n to the s. Suppose that it's absolutely convergent for real part s bigger than 1. Okay. Then put a of x equal to summation n less than x is of n. Then we can buy Abel again. Summation n going from 1 to infinity, a of n, a of n, a sub n over n to the s. Now I'm just going to skip a step because I just did it already. N less than x I should do and take limit as x goes to infinity. Okay? Okay, let's do that. Let me not jump the gun. N less than x is going to be a of x over x to the s minus the integral from 1 to x a of t over t to the s plus 1 dt, and there's an s and there's a plus 1 there, right? That's basically redoing what I just did for the Riemann zeta function. And this is valid for real part of s bigger than 1. Okay. Suppose a of x is equal to alpha x plus O of x to the theta, with theta less than 1. Supposing I have some information about the partial sums, because that's the kind of stuff that we used earlier. We knew that the counting function of 1 up to x was greatest integer of x, of course, which was equal to x plus O of 1. We use that, okay? So we use that property. So supposing I relax that a little bit and say that it's O of x to the theta with theta less than 1, and shove that back in here, and then take the limit as x goes to infinity. Okay, so let's do that. I will leave it to you to do it. But if you do it, you will find that this gives summation n going from 1 to infinity, a of n over n to the s equals alpha s over s minus 1. Was it a plus or a minus I had before? Minus, I think, right? Minus 1 to infinity s. So maybe I shouldn't have called this O of x to the theta, but anyway, let's call this a of t minus alpha t over t to the s plus 1 dt. So the whole thing, as before, if you plug it in, you will end up showing this in its generality. Okay? If you have done this in generality like so, what happens is now this factor here is O of t to the theta, and so as long as real part of s plus 1 minus theta is bigger than 1, this converges absolutely. In other words, if real part of s is actually bigger than theta, this converges absolutely. So this defines an analytic function in this region. And it's nice because theta is now less than 1. So the original Dirichlet series which you had, which made sense only in this region, has been analytically continued to a larger region. And according to Riemanns philosophy, the analytic continuation holds the secrets. Therefore, you're now well on your way in trying to understand the function that you have, that a sub n. Okay? So now why didn't I rub this off? It's because deliberately doing this, because here we have psi of x is the partial sum of lambda of n by our earlier notation, correct? And so if I were to apply this philosophy, well, let's say psi of x equals let me not do it too fast, okay? One important point is to keep in mind that from here itself, you can see that if a of x is O of x, if a of x is O of x, okay, psi of x was O of x, we already knew that. If a of x is O of x, you can take the limit as x goes to infinity and this goes to 0, and you'll be able to write in general not just this, but you'll also be able to write s times integral 1 to infinity a of t over t to the s plus 1 dt, right? I mean, so that this part of the fact is also very interesting in its own right, because you're able to take your Dirichlet series and write it as an integral. Okay. And if you were interested in the error term from the main term and want to study that, this is also useful. Okay, now let me just backtrack a second and try and highlight this particular equality and then stop for the day. Is it almost time? Yeah, it's almost and over. So from here, we see that this can be written as so the prime number theorem is trying to say psi of x is asymptotic to x. I'm interested in knowing the behavior of psi of x, but sadly, psi of x is the integrand in this thing, and I'd like to somehow solve for psi of x. See, so this function zeta of s, which Riemann says holds the key to the study of prime numbers, is being expressed as a transform of the function I'm really interested in. And so somehow I'd like to take the inverse transform, and the inverse transform would involve some sort of this function as the integrand, and therefore the singularities, the behavior of that function is of course going to factor in to determine the behavior of this. So that's the philosophy behind this whole analytic continuation idea. That's what we'd like to do. But if you were to say psi of x equals x plus O of x to the theta, let's say, so if, it's a big if we have this, then this identity here will tell us that minus zeta prime of s over zeta of s is again equal to s over s minus 1 minus s integral psi of t minus t over t to the s plus 1 dt. And this being O of t to the theta would tell me that this is analytic for real part of s bigger than theta, which would mean that the left-hand side is analytic for real part of s bigger than theta, and therefore there are no zeros of the zeta function in that region, real part of s bigger than theta. So if I'm trying to show the Riemann zeta function has no zeros in the region real part of s bigger than theta, that would follow if I could prove a very good error term on the prime number theorem. Remember what the prime number theorem eventually was showing, psi of x is x plus little o of x. But if I could get x to the theta with theta less than 1, I would then deduce that there are no zeros of the zeta function in that region. Now conversely, if I apply this inversion technique, like Fourier inversion or Laplace inversion, what have you, and that's similar in here, it's called Mellon inversion, we'll come to that later. If you apply that inversion formula, then I would say psi of x is equal to the Mellon transform of zeta prime of zeta, right? And if I knew that the zeta function didn't vanish in this region real part of s bigger than theta, I'd be able to conclude psi of x actually is equal to x plus O of x to the theta. So this fact here, the behavior of psi of x with an explicit error term is equivalent to saying that the Riemann zeta function has no zeros in the region real part of s bigger than theta. So the non-vanishing of the Riemann zeta function in the particular region translates itself as an error term in the prime number theorem. Conversely, if you had an error term in the prime number theorem, it translates itself as a statement on non-vanishing of the zeta function. So Riemann was right. The behavior of the zeta function holds the secret for the distribution of prime numbers. That's the philosophy behind behind this. Now, since I'm running out of time, I will perhaps continue next day. This is already pretty good progress. Lots of wonderful things that can be done with respect to many other questions related to prime numbers that we can discuss next time. Sometimes you can use elementary methods, but sometimes elementary methods fall short. And sometimes trying to prove things in an elementary fashion as opposed to using complex analytic tools may be more hard than you think. Elementary does not mean easy. So when people talk about the elementary proof of the prime number theorem, it's not an easy proof. In fact, the complex analytic proof is probably better and faster than the elementary proof of the prime number theorem. Okay, so for today, I think this is a good place to stop. Mull over this, do a few of those exercises that I told you over the weekend, and then we can continue on Monday. For the time being, I can take any questions if you have on the material I just talked. Okay, so we'll take it there from there.